This is the first roller coaster problem in my roller coaster problem packet. Uh, you have a roller coaster that at the beginning is already moving, so just be aware that it's already moving here. And she is designing a scaled model of an actual roller coaster and she wants to test it out. So on this model, a car of a mass 0.5 kilograms moves with negligible friction. So that means no work is going to be done because there's no friction. Along the track as shown in the figure above, the car is given an initial speed of 1.5 meters per second at the top of the first hill of height 2 meters. Point A is located at a height of 1.9 meters at the top of the second hill, the upper part of which is a circular arc of radius 0.95 meters. Calculate the speed of the car at point A. All right, so the first thing that we're going to want to do is we need to create a energy bar chart because I feel like this really will be helpful, especially as we work through the problem. So we're going to have kinetic energy, gravitational potential energy, and work on the left, and then just kinetic and gravitational potential on the right. So at the beginning, it is moving. So I'm going to say it has this much kinetic energy. And it's also at a height of 2 meters. And I don't know which one's bigger, but I'm going to just guess. So for funsies. And then because it's negligible friction, that means work will be 0. And then at the top of A, I want to know how fast it's going. Well, if it's lower, that means it's going to be going faster. So I'm going to say it has this much kinetic energy, which means that it'll have to have less gravitational potential energy. So now I'm going to turn this visual equation into an actual equation. So we have kinetic energy is 1/2 mv squared. Gravitational potential energy is mgh. And then on the other side, we have 1/2 mv squared and mgh. Now just make sure that when you're doing these, you're using final velocities and initial heights and velocities. So you're just being careful about that. All right, so now we just need to plug in the numbers. So the final height was 1.9. Mass is 0.5. Starting velocity was 1.5. And starting height was 2. Okay, G is 9.8. All right, so we know everything except for that final velocity at point A. So maybe I could even say velocity A and height A. Either of those work. All right, so now I'm going to plug in all of those numbers. I can cancel out the masses if I wanted to. It doesn't matter. This time I didn't, just because I don't feel like it. Okay, so now I have all my numbers calculated. Now I just need to do a little bit of algebra. All right, so we get a velocity at point A of 2.052 meters per second. So when you're dealing with roller coasters and stuff like this, you're going to have two different heights. You're going to have velocity stuff happening. And so you're using conservation of energy for this. Okay. On the figure of the car below, draw and label vectors to represent the forces on the car at point A. So if I'm thinking about this point A, at this point, which direction is the center of the circle? Down. So if I'm moving in a circle, that means that I am accelerating towards the center of that circle, which means I need more force down than I have up. So I need to have more gravitational force than I have normal force. Now, that doesn't mean that my gravitational force changes. My gravitational force is always mg, but then I will have to figure out what this normal force is. But the important thing being is that normal force must be smaller than my gravitational force at the top of that circle. So on here, I'm only going to put Fg and my normal force. And I'm going to make it obvious that normal force is less than Fg. So in part A, if there was friction, this work would not have been 0. Part C, now it says calculate the magnitude of the force of the track on the car at point A. In other words, I'm looking for what Fn is equal to. Okay, so thinking about this, I'm going to kind of write it up here and then I'll do it down there. So I'm going to have the sum of my forces. Remember that the sum of the forces always have to be towards the center of the circle. Because when I do the sum of my forces, it needs to be equal to ma. And acceleration to go in towards the center of the circle is v squared over r. And there is no way to ever get a negative acceleration to go towards the center of a circle. So you have to make sure that your force diagram accounts for it. So that means I'm doing plus Fg, because that's towards the center of the circle, minus Fn, because that's away from the center of the circle, is equal to mass times the acceleration towards the center of the circle. And now we need to plug in numbers. So gravitational force is m times g. Normal force is what we're trying to find. And then we have mass times, and then the acceleration that we have is because we're going in a circle, it's v squared over r. And we got to put in the numbers. All right, so we're going to use that velocity from part A. Otherwise, all of the numbers are given in the problem. All right, cool. So I subtract the 4.9 from both sides. And then I get negative Fn is equal to negative 2.684, which gives me a normal force of 2.684. Yay! All right, so now it says in order to stop the car at point A, some friction must be introduced. Calculate the work that must be done by the friction force in order to stop the car at point A. All right, so I'm going to go back to my original thing up here. All right, so originally we had kinetic energy at point A because it was still moving. But now it says we need to have it not moving at that point, which means my kinetic energy is going to be 0. So in order to make it stop, what we're going to have to do is we're going to have to add some friction. So this is going to be the work from friction. And this work from friction is equal to the force of friction times distance. But we don't care about that. We just care about how much work it is. And so the work is going to be negative because it's going to be removing energy from the system because it needs to make it slow down. And then we just can plug all the rest of the numbers in the way they were. So I'm going to go up here and I'm going to steal it all. Correct. Yeah. Work is only always on the left side because it's like how much you start with and then how much it changes is going to be equal to how much there is at the end. Yeah. You can do a plus or a minus. It doesn't matter. Yeah, if you guys want to do minus, we can do minus. That sounds good. Sure. I'm happy because it's negative. Sounds good. Because then if I have numbers that I put in, you're right. I would probably do it as minus. Okay. So then I just need to solve. All right. So then I get a work of 1.0525. So the only thing that I changed from part A is that I added this work piece here. And the velocity at point A changed to 0. Otherwise, all the rest of the numbers are all the same. And then I'm just solving for work. And what are the units of work? Joules. So it's the same unit as energy, which makes sense because it's equal to how much the energy changes. All right, now it says explain how to modify the track design to cause the car to lose contact with the track at point A before descending down the track. Justify your answer. All right, in your groups right now, how could you get it so that this car, as it goes over the bump right here, it's going to go wee instead. Ready to go. The first thing that we need to talk about is what does it mean when you are losing contact with the track? Well, at that point, if you're going over the top of the hill, that means that if you are losing contact with the track, that means the track is not pushing up on you anymore. It's not that you have a bigger normal force, it's that your normal force is now 0. So that means that the only force acting on you at this point is going to be Fg. Now there's 2 ways to do that. One of them is that if you think about your sum of your forces in the y direction, or towards the center of the circle, I should say, in this case, it's only equal to Fg. So that's equal to your mass times v squared over r. Well, Fg is mg. So there's 2 ways to change this. First of all, I'm going to notice that if I divide both sides by m, that the m's cancel out. So it doesn't matter what your mass is, you will experience the same phenomenon regardless of how big of a person you are when you go over the hump of this track on the roller coaster. Second, if I want to make this happen, that means that I need this side of the equation, I need the right side to be bigger. So to make the right side bigger, we can do 2 things. One is you make the velocity bigger. How are we going to make the velocity bigger? Good. So make initial hill taller. Good. Decrease the radius of the bump. This makes sense. If you guys have ever gone over a speed bump, there's those really giant speed bumps that are like really huge, wide, like you can like have a whole crosswalk on the top of the speed bump. You know what I'm talking about? And then there's the little speed bumps that are like a foot wide and like 6 inches tall. Okay, those ones, you will feel your car go ka-chunk and the tires leave the ground unless you're going really slow. Yes, the district office speed bumps. That's exactly what they're like. Yeah, exactly. So if you make the radius smaller, you have to go really slow to get over it without flying off your seat. So those are the 2 answers.